So, hello everyone, I'm Amit and I am a postdoc in Stat Physics Condensed Matter group. So, I'll be talking about our recent work on photon self-trapping in a cavity-QED array. So, as shown in the schematic, we arrange identical cavities in an 1D lattice. The cavities are tunnel coupled. In addition, each of this cavity contains quantized light modes, that is photons. And there is this embedded two-level system or the qubit, which is coupled to the photons via this intensity G1. And to take account a realistic situation, we also allow photon loss via this kappa channel and spontaneous decay of the qubit via gamma. Now, if we think of a single cavity is dictated by Jaynes-Cummins interaction. So the last term is basically represents coherent exchange of energy between cavity and qubit modes. So here I take a single cavity with 2 photon content, and for an idealistic situation we suppress all the decay channels and the drive. And here we see the cavity and qubit oscillates in an out of phase fashion. So whenever the qubit reaches an excited state, there is a dip in the photon content. So these are basically the Rabi oscillations. And interestingly, the frequency of the Rabi oscillation scales as square root of n, that is square root of excitations. So this is the signature of anharmonicity, which is inherent in the Jaynes-Cummins interaction. So if we take uncoupled cavity qubit system, so the energy levels are equally spaced, just like simple harmonic oscillators. Same for downspin and the photons. So now if we introduce the Jaynes-Cummins interactions, the separations are scaled as square root of n plus 1. So these are basically polaritonic states. So the anharmonicity or the nonlinearity is obvious here. Now, in the dispersive regime, perturbatively one can introduce a photon-photon interaction in the Hamiltonian. So to begin with, there is no photon-photon interaction, but 2 photons can talk to each other via this cavity-qubit coupling G. And this anharmonicity is strongest when we consider a resonance situation. So now our focus will be this particular regime where strong coupling is considered and there is resonance between cavity and qubit. So this is our full Hamiltonian of the 1D chain of cavities. And the last term is basically photon tunneling between nearest neighbors. And we also allow this various decay channels that leads to non-unitary dynamics. And to study the open dynamics, we use Lindblad master equation where D is the respective dissipator for decay channels. And we also employ a coherent photon drive by adding this term. Now we consider this 2 cavity case. So the situation is dissipative and weak light matter coupling. So we launch the system such that there are 10 photons in the first cavity, 10 photons, and right cavity is empty. So here we don't see any photon self-trapping. The Z is defined as population imbalance divided by total number of photon. So here you see Z just oscillates a couple of times and then decays because of dissipative effects. And next we increase the light matter coupling here and we see a small plateau here. So this is basically the signature of photon trapping or photon self-trapping in the first cavity. But because of dissipative effects, it decays to 0. So here the photon localization remains as a transient effect only. So now we ask this question, how to enhance the lifetime of photon localization. So the immediate remedy is to drive the photon content of the system and attain a steady state, self-trapped steady state. So in this situation, we drive only the first cavity where we want to localize the photons, and we attain an indefinitely sustained self-trapping. So this will exist forever. So by employing drive and dissipation and light matter, choosing light matter coupling, we have indefinitely sustained self-trapping in the system. Now, one can ask if any arbitrary drive gives us this self-trapping state. The answer is no. Here we plot this black and cyan lines for moderate drive, and this magenta and yellow are for a very strong drive. So here you can see if we use a very strong drive, the localization of photon is degraded. So this clearly indicates that there exists an optimum drive window that gives us best photon localization. And we also chose various initial states for photons as well as for qubit. All of them lead to same steady state. So basically this initial state independence is experimentally more feasible. You can start with any initial state and reach a steady state which is self-trapped. And this steady state is basically dictated by the parameters drive, dissipation, and light matter coupling. So now we go for a larger lattice of cavities. Here we take 4 cavities for a quantum case, and Z is defined as summation of odd population minus even population divided by n. So here also we see similar physics. So we drive only the odd cavities, first one and third one, and we achieve a self-trapped situation for a driven case. So now to take account a larger system, we use semi-classical treatment in the large n limit, large photon number limit, where we neglect the quantum correlations and express the second order expectation as the product of first order expectations. And here we take a 1D lattice of 100 identical cavities. So here you can see when the situation is undriven, D is 0, the localization of photon is limited. And we truncate our simulation here because further oscillations barely gives any insight, physical insight, because the self-trapping is already broken. Now, if we increase the drive to 0.04 and 0.1, we have indefinitely self-trapping. But interestingly, when we increase the drive further, D.12 here, again the lifetime of self-trapping is limited. So this also indicates there is an optimum window for good drive. Now we semi-classically obtain this phase space in drive kappa layout by keeping all other parameters fixed. So in the yellow region, we have a self-trapping steady state, and in the blue region, which is a non-self-trapped region. So we divide the phase space into 3 regions, 1, 2, and 3. And in first region, we get a dynamics which is dissipation dominated. So the population decays monotonously, and no self-trapping is there. And for yellow region, we have long-lived self-trapping. And in the phase 3, we have an overdriven case. So initially, the driven cavity increases in its population, stabilizes, and at some point it's dynamically delocalized. So in the inside, you can see the intercavity tunneling sets in. And if we increase the drive further into this phase 3, the localization lifetime is reduced. And we also give a theoretical estimate for this upper boundary D1 max that demarcates the 2 phases 2 and 3. So I conclude. So we have shown that delicate balance between drive dissipation and strong light matter coupling gives us steady state self-trapping. And we also addressed an extended version of cavity-QED lattice, where we can see self-trapping. And this kind of architecture has already been experimentally realized in a coplanar waveguide with 72 cavities. And this self-trapping physics has relevance in controlled photon transport in quantum communication networks. So in this regard, one can ask the nature of localization in 2D arrangement and whether it depends on coordination number. Thanks for your attention.
Thanks, Amit. Questions? So if there are no questions, then let us thank the speaker again.